In this video, we introduce a special type of function called an inverse function. What are they? How do we find them? And how do we check if our functions are truly inverses? Let's get started and find out. So recall that a function is a relation in which every input gets mapped to exactly one output. For example, f of x equals the square root of x. If you input 16 as your x value, you output 4. If you input 4 as your x, you output 2. If you input 9 as your x, you output 3. So that's definitely a function. But I would also claim that that is a one-to-one function. The reason? Every input maps to exactly one y output. But that y output is uniquely determined by its input. In other words, there are no shared y values among different inputs. On the other hand, take a look at the function g of x next door. In g of x, it equals x squared. Now we know x squared is a function. It's actually the parabola opening up, right? That's a function which passes our vertical line test. Every input gets mapped to exactly one output. So let's take a look, for example, at the input of 3. If you input 3 into the function g of x equals x to the second power, you get negative 3 times negative 3, or 9. If you input negative 2 times negative 2 is 4. But if you input positive 2, you also get 4, don't you? Or even if you input positive 3, you also get 9. So this is a case where multiple inputs generate the same output. In other words, y values are shared by different x values. If that's the case, we would declare this function just a regular function, not a one-to-one function. So what does it mean to be one-to-one? Every x value gets mapped to precisely one y value, and that y value shares no other inputs. And that's what you see in your definition in the right-hand corner of your notes on the screen here. It says for every input, there is exactly one output, the definition of a function. Additionally, though, every output has exactly one input which generates it. More simply, you know that a function had to pass the vertical line test, but a one-to-one function additionally will have to pass a horizontal line test, meaning that every single point on the graph of a function, if it's truly one-to-one, will only be touched one time if you draw a horizontal line through it. For example, take a look at the first picture in A. I could draw a horizontal line and only hit once here, but then I hit another time over here. So would this be a one-to-one function? No, it would fail the horizontal line test. So we would say A is not one-to-one. It is a function. It's a parabola, in fact, but it's not a one-to-one function. You might be wondering right now, why would I care? And that's a valid question. But one-to-one functions are going to have special properties, namely, they are able to be inverted. They're invertible. And we're going to need that skill as we move on in our math classes. For B, on the other hand, it almost looks like a sine wave or a cosine wave that we'll study in a trigonometry class. And in this case, we notice that we are, again, failing the horizontal line test. There are multiple places where that horizontal line would touch this graph. Finally, we're down to C. In choice C, we have a situation where we have a line with a positive slope, and I could put a horizontal line anywhere along that graph and only hit one time. This would be the one and only time in this graphic where we have a one-to-one function, meaning every x has precisely one y value, and every y value was generated only by that one x value. So in the blank here, one-to-one functions must pass both the vertical and the horizontal line test. Okay, so if you pass them both, you are one-to-one, meaning your function is invertible. It has an inverse. So let's head over to our next slide where we continue this topic. In example 1, it says, could you determine if the functions below are truly one-to-one functions? So take a moment and pause the video, see if you truly understand the definition, and pick which one of these, if any, are one-to-one. Okay, let's see how you did. In A, every x value, your domain, 1, 2, 3, 4, gets mapped to a y value, it looks like. For example, the input of 1 creates the output D, the input of 2 creates the output B, the input of 3 creates the output C, and the input of 4 also creates the output C. Would this be a function? Sure, every input gets mapped to one output. But is it a one-to-one function? No, that's because C is shared, or it's found by multiple x values. So we would say this is not one-to-one. B, on the other hand, would that have been a one-to-one function? It's definitely a function, right? Every input gets mapped to precisely one output. But are the y outputs shared by any other x values? No, they're not. They're all distinct, aren't they? D only gets created by the 1, B only gets created by the 2, and A only gets created by 3. So this is 1 to 1. Now what's the point of this? In a few minutes, we're going to talk about how we can invert the function by switching the x and the y values. And that would only make sense if they only have one partner. Okay? So this is our faithful function, unlike other relations which have multiple shared partners. Now for C, y equals x cubed, we have the snake, the vertical snake, x cubed here. Would this be a 1-to-1 function? Well, it's definitely a function. It passes your vertical line test, but look at that horizontal line that they put there for you. It's definitely not going to have any problems at that location. How about at this location? Still, no problems. How about at this location? No problems. You could put a horizontal line anywhere on that snake, and it would only cross an output one time. So this is an example of a 1-to-1 function. What about the other snake, though? Y equals x cubed plus 3x squared minus x minus 1. Look at its graph. Well, you can already see the problem, right? With the line that they've drawn, it shows you that there are 1, 2, 3 places where that graph gets crossed by a horizontal line. Now, maybe you're a little more clever than them, and you think, I'm going to put my horizontal line up here, and it's only going to touch one time. But just like for the vertical line test, it has to work anywhere you would place that line, right? If you put a horizontal line anywhere on this graph, it should only cross once if it's truly a 1-to-1 function. So we would say, no, this is not 1-to-1. So once again, 1-to-1 functions must pass the horizontal line test because every input is mapped to exactly one output who does not share any other x values. Let's take a look at our next slide. So what is the point of having a 1-to-1 function? Like we've mentioned, a 1-to-1 function, f, is going to have an inverse function. So that's our first blank here. It will have an inverse function. So if the original function's name is f, the inverse function is read f inverse. And the way we write that is f superscript, so a little power, or like almost an exponent, -1. That doesn't mean 1 over f. In fact, you might want to write that in your notes. That is not the same as 1 over f, the reciprocal of f. Definitely not the same. It's a notation that we're going to use for the inverse. So when we see the -1 up there, we will think this is the inverse of f, or f inverse. What's the point of this? Well, suppose you look with me at the graph on the left side of your screen or your notes, and you notice that you have this curve here, and we're calling this curve y equals f of x. So it's a nice growth curve. Maybe it's exponential. We'll study that in a future video, okay? So this particular growth in blue is known as f of x. Now, would you agree with me that this is a 1-to-1 function? Would it pass the horizontal line test? It would. So this function is 1-to-1, meaning it is invertible. It has an inverse. So why do you think I drew, or they drew, the inverse function to be this orange one down here? Something like this, where they say this is now called y equals f inverse, okay? Well, the reason they know that is because what they've done is they've taken the x value and the y value of the original function, and they've switched them. That's what it means to invert a function. It means to switch the x and the y values. In the next couple videos after this one, you're going to study exponential functions, which kind of look like this blue graph, and logarithmic functions, which kind of look like this orange graph. And what they are inverses of each other. They undo each other because they are switched at the x and the y. They are switched at the domain and the range. So for example, if in the blue graph of f of x, that looks kind of exponential to me, if that x value, let's say, was at 2, 3, what do you think the x and the y value would be for its inverse? There you go. It would be 3, 2. So now you have that point there. So that's what we're doing for every point on that graph. You're switching the x and the y value. The output and the input have switched. What happens if you have an inverse function is a couple of really cool properties. One property that's neat is that their graphs should be folded over or the same distance away, like a mirror image, along the line y equals x, the identity function. You'll always have this type of symmetry along the line y equals x, meaning I'm the same distance away from that line. So if I was trying to graph an inverse function, I would simply switch my x and my y and make sure that my graph is symmetrical about that line. So that's pretty awesome. And that happens because we've switched x and y, so they're the same distance away from each other. Now, another thing I've mentioned already is that if you've switched x and y, your domain and your ranges have swapped in the function's graph. So the domain, the x values for the original function, are now the y values for the inverse function. So the domain of f equals the range of f inverse. Similarly, the y values, or the range of the function originally, is now the domain of the inverse function. So if you're going to truly have an inverse function, their domain and their range should have swapped. Okay? And finally, one more trick. If you're not looking at the graph, but rather the equations, to undo each other means that the operations undo each other. What I mean by this is a function is really a set of operations. For example, if I have the function f of x here equals 3 minus 2x, in order to get an output for this function, you input a number, you multiply it by -2, and then you add 3. That's what you're consistently doing in order to get your outputs. You know an input, you put it in, you multiply by -2, and you add 3. But if I wanted to undo that procedure to get back to my original input x, what would I have to do? And that's where the inverse function does. It allows you to undo the function's operation so that you're back to the original input x. In other words, it's function composition. In our last video, we talked about you can stick a function inside of another function, right? F of g of x. Here we're saying if you stick f inverse inside of f, or f inside of f inverse, you're going to just get x. They're going to basically cancel out. That's a very simplistic way of looking at it, but it's almost as if this negative and this one that's positive are canceling, and you're left with just x. Okay, so that's one of the ways you're going to be able to check that you have inverses. When you put them inside of each other, it should just undo the original operation, leaving you with the input x. Here's what I mean. In the function f of x equals 3 minus 2x, and the other function, g of x equals -1/2 parentheses x minus 3. If these are truly inverse functions, one way to check is if I put them inside of each other, they should undo the operations and give you just the input x. So let's try the first one. If I want to check if they're inverses, I'm going to check if f with g inside, f of g of x, if that truly gives me just x. So let's practice that. We would start, if you remember from the last video, with the outside function, which says take 3 minus twice your input x. But instead of x, the input has been replaced with what? That's right, g of x. G of x here was -1/2 parentheses x minus 3. So carefully do your arithmetic. Feel free to pause the video and see if you only get x. So in this case, when I distributed -2 times -1/2, I just get +1. So that's one way to do it. But most students, they probably would have distributed inside first, and that's perfectly appropriate. So you would have had 3 minus 2 copies of -1/2 x and +3/2. So what would that have generated then? Well, distributing the -2 now, you would have -2 times -1/2, which is +1x, so 3 plus x, 1x, right? And then -2 times a +3/2 gives you -3/1, because the 2's cancel. In other words, -3. Feel free to slow yourself down there if you need to write it out. The 3 minus 3 cancels, and guess what? I'm left with the original input. So f undoes the g operation, so you're back to your original x values. Now, does g undo f? Let's see. If I plug in f inside of the g function, I better get x. So go ahead and pause the video and try it yourself. What is g of f of x? Well, that's right. You'd start with the g function, which was take -1/2 times your input x and subtract 3. But this time your input x has been replaced by f of x, where f of x was 3 minus 2x. So this has replaced your input, where x used to be. Go ahead and do the arithmetic if you haven't already. Okay. Inside those parentheses, you would have 3 minus 2x minus 3. Well, the 3's cancel. Now I just have -1/2 on the outside, and on the inside, -2x. But what happens when I multiply -1/2 times 2? That's right, I get a -1. But since it's a -2, I actually get a +1. And that's +x as my answer. So since g undid f and f undid g, they truly are inverses. So we have confirmed that f and g are, in fact, inverse functions. They're inverses of each other. Now, perhaps you're planning on going on in math to a pre-calc or a trig class, this is going to be one of the most essential concepts of your future math success, really. You really need to understand the idea of undoing things. You already know basic principles of this. For example, to undo addition, you use its inverse, subtraction. To undo multiplication, you use its inverse, division. And here we're saying to undo a function, you need another function called the inverse function. Okay, so let's see if you can practice checking this yourself on the next slide. Verify that f and g are truly inverse functions, where f of x is the rational function, a fraction, x minus 5 over 2x plus 3. And g of x is another rational function, 3x plus 5 over 1 minus 2x. It's a little harder, but it's the same concept, so I'm going to encourage you to try it yourself, pause this video, and then come back and see if you did the same thing as me. So to check if two functions undo each other or are inverses, what did we do again? That's right, we said, does f of g of x give me x, and does g of f of x give me x? So let's take a look. If I input the g function into the f function, I would have the following. I'd start with my f function, which says take something minus 5 divided by 2 times something plus 3. Notice I like to use parentheses for my input, right? Because I'm replacing my input now with the rational function g of x. So g of x is replacing my x value. That's a tricky step for many students, so make sure you pause the video if you need to. So this would become g of x, which is 3x plus 5 over 1 minus 2x in both places. Now, what bothers students here is the overwhelming amount of fractions, and I understand that Americans hate fractions, but if we're going to grow in our abilities, we have to overcome that fear and persist. So let's continue by remembering, how did we add or subtract fractions? That's right, we had to get the common denominator, and in this case, it is a 1 under the 5 and a 1 under the 3, and a 1 technically under the 2. So in order to get a common denominator, you would take the first denominator completely, and then only new factors of the second one. So in this case, 1 minus 2x is your LCD, your least common denominator, which means, if you remember from your previous math classes, you might need to go back and review some topics, that this is just 1 minus 2x as my least common denominator for the numerator of this complex fraction. But for the first piece, for this piece, I already had that denominator. So I just copy the numerator. It was 3x plus 5. For the second term, it was negative 5. But that negative 5 needs to be multiplied by something because it did not originally possess the right denominator. In order to get that denominator of 1 minus 2x, I would have had to multiply the top and the bottom, which is 5 and 1, times 1 minus 2x. So you'd put 1 minus 2x in both places. I'm simply skipping a step of writing that out. But if you need to, feel free to do that. So this is now 1 minus 2x because that was the missing denominator of negative 5. Okay, we'll come back to the arithmetic there, but let's head over to the bottom half of this complicated or complex fraction. Similarly, the LCD for these two terms is in fact 1 minus 2x. Now that is very providential. We are in good shape because of this. I'll show you why in a moment. Maybe you've already figured it out. For the first term, it already has the right denominator of 1 minus 2x, so I get to just copy 2 times 3x plus 5, or if you preferred to distribute there, you could have already done so. But for the second term, the positive 3, notice what I have to do. His denominator was not already 1 minus 2x, it was just 1. So I would have had to multiply top and bottom by 1 minus 2x. Feel free to write that if you need to. Now I have 1 minus 2x next to the 3, and the denominator is now appropriate. Okay, so if I now have this nasty complex fraction, one of the reasons it's so nice that I have the same denominator here as I do down here is because when I divide two fractions, if you remember, you're really multiplying the first fraction by the reciprocal, or keep, change, flip, I think they say in Florida. You're multiplying the first fraction by the reciprocal of the second, which means 1 minus 2x will be on the top and on the bottom of the two different fractions. They cancel out. So the shortcut is just to cancel the denominators at this step because they're identical. Meaning, you're only going to have the top numerator over the bottom numerator as your fraction. So let's take a look at the arithmetic here. If I distribute the negative 5 carefully, I have 3x plus 5 minus 5 plus Negative 5 times a negative 2 is a positive 10. Interesting. And in the denominator, if I distribute my 2 correctly, I have 6x plus 10. And if I distribute my 3 correctly, I have positive 3 minus 6x. Now notice what this means. When we cancel out like terms, we'd have this constant and this constant canceling out, wouldn't we? Positive and negative 5 are gone. But also 3x can add to 10x to give me 13x in my numerator. Looks kind of nasty, but let's continue. Maybe you already see a pattern. 6x minus 6x, death to you, death to you. They cancel out. And then we just have 10 plus 3, which is 13. Is that good or bad news? Well, that's great news. The 13s cancel. I'm left with just my input x. So what we've just checked is whether f undoes g. And the answer is yes. F function undoes the operation of g on the input x, bringing us back to x. What I would encourage you to do is check the other direction on your own. And if you get stuck, feel free to contact me, come by my office, or email me. But I would like for you to try g of f of x. It's exactly the same procedure. I'm going to set it up, and I hope for you to finish it on your own. So I would begin with g as my outside function, which says take 3 times my input, add 5 over 1 minus twice my input. What's going to go inside there? Do you know? Yep, you're right. The f function, x minus 5 over 2x plus 3 in both cases. So see if you can go from here. You might need some help with your fractions, getting the like denominator and such, but eventually you better just get x. And that's how you can confirm that not only does f undo g, but g undoes f, meaning they are truly inverses of each other. Okay, so on our next slide, take a look at what we're talking about. We are giving you a function f, and it's this nice blue curve, and we're asking you to recognize if it's 1-to-1. Is it? Yes, it passes the horizontal line test. If so, could you draw its inverse? That's what it's asking, right? Well, if you're trying to find an inverse, f inverse, what do we have to do to our x and our y values? That's right, we have to swap them. So we notice that in the original function, they've given me at least one x value there. That's an x value of 1 and a y value of 0, right? Have they given me any other ones? I see one. How about 2 for x and 1 for y? Okay. At least those 2 points would be helpful. So now can you go ahead and try on your own? It's a very easy problem, I hope. Can you switch the x and the y values and draw the right picture for f inverse? Go ahead and try. Well, if you did, your 1, 0 would become 0, 1. So that would be this location, 0, 1. And your 2, 1 would become 1, 2, which would be here. So now I notice, remember how the graph of the blue function was getting closer and closer to x equals 0? I bet that the graph of my inverse is getting closer and closer to y equals 0, the horizontal line or the x-axis. And look what happens if I graph. It does look something like this, and I could continue checking more and more points if I wanted to be precise. Notice that they should have symmetry along the line y equals x. If they're truly inverse functions, they should be reflected over that line the same distance away in both directions. How do you answer questions about domain and range? Well, what would be the domain of the original blue curve, f? You're right, any x value to the left of 0, it looks like you're getting closer and closer to 0. So that would be parentheses 0 toward infinity, meaning any x value bigger than 0. But wouldn't that also be the range of f inverse? Let's see. Would that be the range of f inverse, 0 to infinity? Well, yeah, isn't it values above the y-axis, the x-axis, which is y equals 0? Yeah, it's above 0, so that would be the correct range. How about the range of f itself? Well, the range of f appears to go down forever and slowly up forever. So that would be negative infinity to infinity. Well, that should be the domain of f inverse, the x values of f inverse. Well, let's take a look. Which x values are allowed for my red f inverse? Left forever and slowly to the right forever. That is negative infinity to infinity. So interpreting infinity symbols might be something you need to work on. When it's an x value, negative infinity to infinity means left forever, right forever. When it's a y value range, negative infinity to infinity means down forever and up forever. So make sure you interpret those correctly, and then it makes sense to use this notation. All right, we have one more thing we need to talk about. We've talked about how do I know if I have a one-to-one function? How do I know what to do if I have an inverse function? How do I graph, etc.? But now we're going to say, how would I find an inverse myself? So here is an example. Suppose you have the function f of x equals negative 4x. So the operation is you take an input x and you multiply it by negative 4. You get your answers. So when I'm asking for an inverse, I'm saying what operation, what function would undo this? And you might already have the answer. For example, if the x value is 2, you input that as x, and you multiplied it by negative 4, you would get negative 8. How would you get back to the original answer of 2? Well, you would have to divide by negative 4, wouldn't you? And that would really be the same as multiplying by negative 1/4. So I bet negative 1/4 x is my inverse. But let's verify that with our step-by-step approach. Step 1, switch x and y. So if you're taking notes, make sure that is your very first step. That's the same thing we did when we had the graph, right? We switched x and y if we're finding the inverse. So what is x and what is y? Well, here the input was x and here the output was y. So if I switch them, step 1 in this case would be x equals negative 4y. Okay, let's go to step 2. Solve for y. This is just you showing off your algebra skills. How do you undo multiplication? Division, the inverse operation. So this would be divide both sides by the number touching y, negative 4. Be sure you know what this means. The coefficient of x here was implied to be a 1. So what do we really have? That's right. We have, as step number 3 here, we're going to replace y with f inverse in the end. We have that y equals negative 1 over 4x. But before we call it a day, we rewrite this equation as f inverse function. So f inverse of x is really take your input x and multiply it by negative 1/4. We're claiming that will undo the original f function. So you could then check if it's true, right? If you input 4x right here, negative 4x right here, and you multiply that by a negative 1/4, they wipe away and you just get x, don't you? And similarly, if you were to input negative 1/4x into negative 4 times that input, you would just get x. So they do, in fact, undo each other. They are inverses, and their graphs would look accordingly. So check out your last example. Can you have these instructions and apply them to finding an inverse yourself? It says find the inverse function of this one-to-one function. F of x equals x cubed minus 1. So for this graph, we notice this is actually representing a snake. It's a snake that's been shifted down 1 unit. So if you remember from your previous math videos and chapters, this graph looked something like the snake shifted down 1 unit. So something like this has happened. And you can clearly tell, if you remember what the graph looks like, you should be able to tell that this is a one-to-one function. So it is invertible. So how would we undo the process of cubing a number and subtracting 1? It might have something to do with a cube root, but let's get started with our steps. Feel free to go ahead and go back to the notes if you need to. Pause the video and try it yourself. Step 1, what was it? Switch x and y. So x would equal y cubed minus 1. What was step 2? That's right, solve for y. So we want to first isolate the cubed term, the y cubed term, by adding 1, because that's the inverse operation of subtraction. Add 1 to the x value. We have x plus 1 now equals y to the 3rd power. So we're talking about step 2. Finally, to get y by itself, we need to undo the operation of cubing something. Well, what's the opposite operation of cubing something? That's right, it would be taking the cube root. So if I took the cube root of both sides, notice I don't need a plus or minus like I would with the square root, because cube roots can have negative numbers, so they're uniquely generated, unlike square roots. So this final answer would just be y should equal the cube root of whatever your input x is, and then add 1. But the way we're going to write that, we said, is that we're going to now call y our f inverse. So step 3, replace y with f inverse. F inverse of x should just equal the cube root of your input plus 1. Now, could I check this? A couple of ways. You could see if you input f inside here as your x, whether you just get x. Similarly, if you input f inverse into x in your original, do you just get x? You could check both ways to confirm that these do undo each other. They are, in fact, inverses. You could also go to a graphing utility and type in the graphs of both of them and watch to see if there is symmetry along the line y equals x. All right, so we've done a lot. In this video, we've learned how to find the inverse, how to check inverses, and what a one-to-one function tells you. So go practice, because math is not a spectator sport, and I'll see you next time.